This video is about the equations in P3, and P3 is the module that above all others contains the most equations, so there's quite a lot to fit into this video. So the first equation that we start with is the equation for speed, which is distance divided by time. So the units for speed are meters per second. Distance has to be in meters and time has to be in seconds. If not, we get different units for speed. Another equation I'm just going to mention that's very similar to this is the equation for velocity, which is still meters per second, and it's nearly the same thing as speed, but remember, velocity is speed in a direction, and the reason for that is because the distance is in a direction, and we call that displacement. Now, it can be slightly confusing that the symbol for displacement is also S. But really it doesn't matter what letter you give it, as long as you understand what it means. But displacement is also in meters, and time is also in seconds. So remember, velocity is speed, but in a direction. The next topic in here that we do is acceleration, which is v minus u divided by t, or acceleration is the change in speed divided by time. So I'm going to use this notation quite a lot. So v is the symbol that we use for final velocity. U is initial velocity. Now, we do quite often interchange the words velocity and speed in P3, largely because as long as the direction isn't changing, they are in fact the same thing. So just be aware of that. Obviously, initial and final velocity are both in meters per second. Acceleration is in meters per second squared, and time is still in seconds. Now, this equation is quite often rearranged when we do the equations of constant acceleration as v equals u plus at. It's exactly the same equation, but it's rearranged, and that's the first suvat equation, which is absent of s. If you don't know what's meant by suvat equations, don't worry, because we do that in P5. So if you're not aware of suvat, don't worry about it. If you're not doing P5, you don't really need to know it, but it is this same equation just rearranged. One of the other suvat equations that's in P3 is this equation, speed is distance divided by time, but rearranged to give us displacement. In this particular case, because we use velocity. Rather than just using normal velocity, we use average velocity. So displacement is u plus v divided by 2. So that's how you'd work out the average speed, average velocity, and then you multiply that by time. That's the suvat equation, which doesn't have acceleration in it. Just for the purposes of completeness, the other suvat equations that we need to remember are s equals ut plus half at squared, and v squared equals u squared plus 2as. This equation comes from the area underneath a velocity time graph or speed time graph, and is missing final velocity, and this doesn't contain time. So like I say, if you don't know what the suvat equations are, don't worry about it, because it's in P5, but if you're doing triple, then you do need to know those equations. The next equation that we do is the equation for force, which is mass times acceleration. So force is measured in newtons, and there are a couple of special cases of this equation. The second one is the equation for weight. Now, weight, remember, is the force due to gravity, so it's measured in newtons. Obviously, it represents the difference between mass and weight. Obviously, mass is in kilograms. And g is the acceleration due to gravity. So this has two names, two common names. Acceleration due to gravity. This other name is gravitational field strength. And you can assume that those two words mean the exact same thing. On Earth, g is equal to 10 meters per second squared. So that is always the case. So remember, as a little fact, it's useful to remember that gravity on Earth is always equal to 10 meters per second squared. Another form of force comes from once we understand momentum, which is one of our latter equations. So momentum is mass times velocity. Momentum has the symbol rho, which is like a sort of slanty p, which is in kilogram meters per second as the units. And because of F equals ma, acceleration can be written as change in speed divided by time. And since mass and change in speed is momentum, we can write that force is equal to the change in momentum divided by the change in time. And that is actually how Newton wrote his second law. Rather than writing F equals ma, he wrote it this way. So force is the change in momentum divided by time. And this is particularly useful because when we deal with momentum, we always associate momentum with collisions. And so it's important that if we're considering momentum collisions that we associate it with that. Now a little aside, for those of you that are doing P5, you need to remember a couple of versions of collisions and momentum equations. This can come up in P3, but it's not likely to be done to this level of depth. So again, if you don't understand this little next bit, don't worry about it. The first example that we've got is I've got two objects that are colliding and they rebound off each other. So I can have m1u1 plus m2u2 will equal m1v1 plus m2v2. So that's when I've got two objects, they collide with each other, and then after the event they rebound and they're going in opposite directions again. Another situation that I can have is when they stick together. So then I'm going to have m1u1 plus m2u2 will equal m1 plus 2, because when they stick together their masses will add together, and v, which is the final speed. And I can have that process in reverse, which is when I have an explosion taking place. So then it will be m1 plus m1 and m2 added together, u, whatever the starting speed is, m1v1 plus m2v2. So again, don't worry if you don't understand those equations because you're not doing triple. Don't worry about it. That's not in, but it's just to make sure you're aware of it if you are doing triple. The next equations that are important for everybody is the equation for power, again, which we've done in P2, which is power, which is measured in watts, is energy transferred or work done, which is measured in joules, divided by time, which is obviously in seconds. And the equation for work done, which I'm just going to show is E, here again, is force times distance. So work done, energy, is force, still measured in newtons, times distance, and it's the distance travelled in the direction of that force. So quite often these two equations can be used together. In fact, in the next topic that we do directly put them together, so we can include these, we can include this equation and the equation for weight to give us the work done due to gravity, which we quite often call gravitational potential energy. And so since we know that work done is force times distance, when we do work against gravity, or I lift something a certain height, then I am overcoming the weight. So gravitational potential energy is mass times g, or the weight, which is the force, times distance, which is the height. So we talked about gravitational field strength. Remember, h is the height. So if I lift an object a certain height, I will give it gravitational potential energy. The next equation that we do is the equation for kinetic energy, which is half mv squared, so half the mass times the velocity squared. Now when you do this equation, make sure you follow the rules of BIDMAS. so that you do velocity squared first on your calculator, then times it by mass, and then divide it by 2. It's useful to be able to practice rearranging this equation because it's one of the hardest equations to rearrange. So just to give you an example, if I wanted to know the velocity, I would have to do 2 times the kinetic energy, and then divided by the mass, and then square root it at the end, because obviously that's v squared. I've got to do the opposite. So there's just an example of rearranging that. Another quite simple equation that we do is stopping distance, which is equal to thinking distance plus braking distance. So that's in car safety. And with braking distance, there's sort of an extra equation that we can sort of add to this, which is that the work done by the brakes on a car is going to be equal to, because it's got to slow the car down, the work done is going to be equal to the kinetic energy that the car had. So that's the work done by the brakes, and that's going to be equal to the braking force times the braking distance, which I've written here as S for displacement. So there's just an extra little equation just for, particularly for AA star students to think about. The work done by the brakes in order to slow the car down is equal to the kinetic energy that the car has, and that will be equal to the braking force times the braking distance. So if the velocity, this shows that if the velocity of the car increases, or if the mass increases, the braking distance will increase if the force is constant, for example. The very last thing in this module is making these 2 equations, gravitational potential energy and kinetic energy, equal to each other, which happens in, for example, roller coasters. So what we assume here is that no energy is lost to friction, and therefore as an object falls, all of its gravitational potential energy is turned into kinetic energy. And that's useful because we can rearrange this, and you can see it's because it's got mass on both sides, that will cancel. So we can get that V is equal to 2gh, but remember it's v squared, so we have to square root it. So velocity is the square root of 2gh. The height, which is another equation that I can rearrange, will be velocity squared divided by 2g. So these 2 equations are particularly important because if you know the height, you automatically know the speed that an object will be falling after it's fallen through that height, and if you know the height, you automatically know the speed. So because the mass is irrelevant. So there's quite a lot of equations in P3, so make sure that you practice them and make sure you use the 4 steps to help you select each one when you're doing your exam.